a simple voltage regulator. We're going to go back to looking at our Zener diode, something that we will investigate further next year, but this year we're just going to use a Zener diode to create our voltage regulator, perform calculations based around that and see what happens when we change the load value and current increases. Okay, so let's first of all draw our circuit. Okay, here we have our circuit. So we've got our Zener diode here in reverse bias. We've got a safety resistance going with it, and then we've got our load resistance. Now that load resistance is actually our load to whatever we're looking to connect to our power supply. The supply to this regulation circuit is from our unstabilized supply. So if we draw a graph of the current flowing through the load against the output voltage, now the output voltage is going to be whatever the Zener diode value is. So if this is a 5 volt Zener diode, then our output voltage will be 5 volts and we'll maintain rock steady 5 volts. However, if we start making this value of load too small and the current increases too much, then what happens is all of the current starts coming down through the load, and there is insufficient then a current then to keep the Zener diode turned on, which means then we basically get a potential divider between the load value and this resistor. So at some point in time we get to a point where then current then starts, so the output voltage then starts to decrease as we draw too much current from the circuit. And we're going to obviously, what we're going to do is we're going to investigate and try and find out about these 2 points here with our calculation. Okay, so we've got these 2 points. So we've got this one here, which is our maximum load current, and this point here defines our safety resistor. Okay, so all we're going to do now is just do a series of examples. So let's start off with this circuit here, 3.3 volts in a diode, so hopefully voltage across the load to be 3.3 volts. So our first question is to you then is, what is the voltage across the 20 ohm resistor? Okay, so that's now a nice easy 9 volts minus our 3.3, which should have 3.3 volts across here, giving us 5.7 volts across our safety resistor. So what's the current through that resistor then? So our current is equal to voltage divided by resistance. So we now know that there's 5.7 volts across it and it's a 20 ohm resistor. So we've got 285 milliamps. Okay. So let's say what's the power rating of that resistor, so that we can see which one we need. Okay, so we've got a couple of ways we can do this. I'm going to use I squared R. We've got 285 milliamps squared times by 20 equals 1.62 watts. Okay, so a pretty reasonable size resistor we need. Okay, nice little simple one then. So what is the Zener current then if our current through the load is 200 milliamps? So we've got an overall current of our total current minus the current through our load. So the total current is 285 milliamps minus the current for our load. There's a current through our Zener diode of 85 milliamps. And if we wanted to, then we could work out what the power rating of the Zener diode needed to be. Okay, one last question with this example. Okay, so our power supply has now changed from 9 volts to 12 volts. That's coming into the circuit. So what's the voltage across the load now? Okay, yes, that's right. It's a bit of a trick question. So it's not changed. Still going to be 3.3 volts, but our resistor got more voltage, so therefore there's an increased power consumption across that resistor that we just maybe need to be aware of. Okay, right. Okay, so our new circuit here, 100 milliamps through the load, 5.1 volts in a diode, and an 8 milliamps holding current. So that's the current required to keep the Zener diode on. What is the value of R? Okay, so first of all, well, if there is 5.1 volts across our Zener diode, then therefore there must be 6.9 volts across our resistor. Therefore the current in our resistor is our total current, so we've got 100 milliamps going one way and we've got 8 milliamps going down through the Zener diode. This is a total current of 108 milliamps. So resistance equals voltage divided by current. So 6.9 volts divided by our 108 milliamps gives us a 63.8 ohms. So we're going to choose it from our E24 series. Do we choose a 62 ohm or a 68 ohm? So we choose our 62 ohm because we need to maintain the holding current. If we increase the resistance, then we would add insufficient current to keep the Zener diode on. Okay, right, let's go on to a third quick example. Okay, so in this third example here, we've been given a graph here, shows our current through our load V out across our load here. So 25 ohm resistor. So the first thing I want to do is work out what is the Zener diode. What is the Zener diode value voltage? Get that from the graph. Look at our graph here, and our Zener diode, until we try to draw too much current, maintains a nice and healthy steady 7.5 volt. Okay, so what is the maximum current through the 25 ohm resistor? We can do this a couple of ways, but we'll see the result. So first of all, just use the traditional method, voltage divided by current. If we assume that, well, the maximum current is when we're going to have no load connected, so we're going to have the whole of the 15 volts. And so 15 volts divided by 25 ohms equals 600 milliamps, which is also, see on the graph there, is our 600 milliamps here. Nothing, no voltage across our load. We've attained that from the graph. So I meant to say there on that one there, where the maximum current is going to be when the load has no resistance, so it's a short circuit. So therefore we purely got the current going through the 25 ohm resistor, and there's no current going through the Zener diode. So no current going through the Zener diode, and the load has ohms. Okay, so now I can say if the load is disconnected, what is the current through the Zener diode? Well, the current through the Zener diode, we're still going to have 7.5 volts across it. So in this case, because I've got 15 volt supply, then we can use our resistor. So current is equal to voltage divided by resistance. So the voltage across our resistor is going to be our 15 minus the 7.5, so it's going to be exactly half anyway. 25 ohms equals 300 milliamps. Can we see that anywhere on the graph, do you think? So what's the power dissipated by the Zener diode? So voltage times current. So we now know that we're going to have got 7.5 volts across it, and we've got 300 milliamps going through it. So we need a reasonable value of Zener diode of 2.25 watts. Okay, one last question associated with this one. Okay, so the load resistance decreases, which causes us the current in the load to be 400 milliamps. What happens to the output voltage? Well, we can see what happens on the output voltage on the graph. We can see that the Zener diode is starting to switch off, but quite simply calculate it, can't we? Because we can say our voltage across our resistor. Then if we've got, because we're going to have 400 milliamps flowing through that resistor as well, we assume that, make the assumption that the Zener diode is switched off, times our 25 ohms equals 10 volts. So therefore our output voltage then is going to be 15 minus the 10 volts that has crossed that resistor, giving us a 5 volt output. Okay, so we could put it all together with a power supply. So we've got 240 volts RMS, 50 Hertz. We've got a transformer there, giving us 12 volts RMS going to a full wave rectifier. We've got a smoothing circuit here, and then we've got a voltage regulator with our phone being. So we'll put a 5.1 volt Zener diode there. So the first question is, what is the peak voltage from the secondary windings of the transformer, the output for the transformer? So we've got a nice little RMS to peak conversion to go with to start with. So we're going to have our 12 volts times by root 2 equals 16.9 volts. Okay, so our peak voltage should be larger than our RMS voltage. So then, now I want to know is what is the peak voltage from our rectifier. Remember, this is a full wave rectifier, so 16.9 volts, and then we've got current's going to be flowing through 2 Zener diodes for each cycle, half cycle, so 1.4 volts. So we're going to have 15.5 volts is going to be our peak output. Okay, so let's see what the voltage across our 12 ohm resistor on our regulator is going to be. I just need to shuffle this up slightly. Okay, so our voltage across our resistor is going to be the voltage going to the regulator minus the voltage across our Zener diode. So 15.5 volts minus our 5.1 volt diode gives us 10.4 volts. Let's find out what the current through that resistor is going to be, and then we can then work out what the power dissipated is. So first of all, I've worked out what the current through the resistor is. 10.4 volts across it divided by its resistance. So therefore my power is going to be I times. So our current in our Zener diode then is going to be, so we've got 867 minus our 700, which equals 117 milliamps. So what's the power consumed by the Zener diode? So 117 milliamps times by the 5.1 volt Zener diode gives us 596.7 milliwatts. Okay, two last things. We need to calculate what the ripple voltage is going to be, so that we can see how that affects our power supply. So our ripple voltage, we need to look at what the current in the load is. Now, if we just scroll back to the original circuit, so the current in our load that we use for our ripple voltage, this whole part of our regulator provides the current in our load. So therefore the current that we originally worked out, which is through the 12 ohm resistor, is going to be our load current. Okay, I know it can be a little bit confusing because you might think, well, this is our load, but it's the whole of the regulator circuit is the load current. So our ripple voltage equals our current in our load, the load being our voltage regulator circuit, the frequency of the ripple, and our capacitance value. So we said that the whole of our regulator is 867 milliamps. I've got 100 hertz ripple and 4,700 microfarad capacitor gives us 1.85 volts of a ripple. Okay, so let's just have one last question associated with this, but what we'll look at is how the ripple voltage may affect our output voltage. So breaking this down, so what is the minimum voltage to the regulator circuit? So if we had 15.5 volts as our peak voltage, if you remember from before, and now our ripple voltage is 1.85 volts, therefore then our output voltage is going to be 13.65 volts. So we can now work out what the current through our resistor is going to be. So we're going to have 8.55 volts across our resistor, so therefore our current in our resistor is going to be 8.55, so the voltage across it, divided by a 12 ohm resistor, gives us 712.5 milliamps. Okay, so do we have any effect then on our circuit? Well, if our load still was required to draw 700 milliamps, then we're going to have then 12.5 milliamps through our Zener diode. If the minimum holding current for our Zener diode, as I said, we wrote down the reason that the question was 10 milliamps, then we've just got enough current to keep our Zener diode operating, which means then we don't have any effect on our output voltage. Okay, and there we have it, just a note to that effect. And then that wraps up our voltage regulators and our power supplies for this topic.